Welcome back everyone. So today we'll discuss another concept from optics, and I have named this as refraction in spherically symmetric concentric layers, and it's just, I would say, that an extended version of Snell's law for spherically symmetric mediums, right? So I have shown here a few spherically symmetric mediums centered at a particular point, and I've shown the refractive index as mu0, mu1, mu2, mu3 and mu4 respectively for the corresponding mediums. And I have also marked the radius of that mediums as r0, r1, r2, r3 and so on. Okay, so and one light ray, I have shown that it is incident from the medium having refractive index mu4 to the medium having refractive index mu3, and it has get refracted following the Snell's law. So I can apply Snell's law at this refraction, and I have marked the angle as θ3, the angle of incidence, and the angle of refraction as alpha here, and I have marked θ2 as the angle of incidence for the next medium, right? So let me first use the Snell's law. So using the Snell's law, I can write mu4 θ3 equals to mu3 sine alpha, right? Because sine θ3 is the angle of incidence from the medium having refractive index mu4, and angle of refraction is alpha, and its refractive index of that medium is mu3. So mu4 sine θ3 is equals to mu3 sine alpha. We're getting this right from Snell's law. And now I will try to substitute sine alpha. So what can I do? I have marked one green triangle in this figure, you can see, and from that green triangle this angle is alpha as already shown, and this angle will be pi minus θ2 because this angle is θ2, the angle of incidence for the next medium. So other side of that line will contain pi minus θ2, right? So I'm using this yellow highlighters, and now I'm applying sine rule in this green triangle. So applying sine rule in this green triangle will give that r3 upon sine of pi minus θ2 is equals to r2 upon sine of alpha. So, and sine of pi minus θ2 is nothing but sine θ2. So from here on we will get that sine alpha equal to r2 upon r3 into sine θ2, this relation. And now I will use this relation further. So this one is the relation, and I have already explained to this step how we have got to this step using Snell's law. Now I have, sorry, not this step but rather this step. This is just simple Snell's law, not even need of some explanation. And now we'll substitute the value of sine alpha here, and we'll get that mu4 sine θ3 is equals to mu3 into r2 upon r3 sine θ2. And just rearranging the terms, we are getting the result or desired result that mu4 r3 sine θ3 is equals to mu3 r2 sine θ2. So what is the significance of this result? I mean, mu into some radius into sine theta is constant. Now let me explain these three terms once. The mu is from the medium the light was traveling earlier. Let's say for this medium it was traveling in the mu4 refractive index medium, right? So here I have written mu4, and it is incident on the boundary of another medium. What is the radius of curvature of that medium? That is r3. So I have written r3 here. And what is the angle of incidence? It is θ3. So I have written the sine of that angle. And for next layer it is also valid similarly, that mu3 r2 sine θ2. Mu3 is the refractive index of next medium, and r2 is the radius of curvature of the next medium of mu3 on which the ray will, on this green marked ray will incident, right? And sine θ2 is nothing but sine of angle of θ2, which is the angle of incidence, right? So I have written like this, that mu r sine theta is constant. In normal cases, what we write, let's say there is one medium mu1 and another is mu2, and let's say this angle of incidence is theta 1 and the angle of refraction is theta 2. We write that mu1 sine theta 1 equals to mu2 sine theta 2. So our conclusion was that mu sine theta was constant for us, and for spherically symmetric mediums we will just include another radius term, that mu r sine theta will be constant. So that's our conclusion, and we'll use this idea over a Pathfinder problem. So let me move on to that problem, right? Yeah, here is the problem from Pathfinder. It is from Challenger Understanding section. Although I have always felt that this problem should not be in the Challenger Understanding section. This is, I think, quite easy once you know the concepts, and it can be framed in check your understanding or build up, but whatever, it is what it is. So that's not our matter of concern. Let's read out the problem first. A laser beam propagates through a spherically symmetric medium surrounding a metal sphere of radius r equals to 10 cm. Refractive index of the medium varies with distance r from center O of the sphere, according to the law that mu as a function of r is proportional to r, right? Here capital R is very less than small r, and small r is less than infinite. So this is well understood, right? The laser beam makes an angle theta equals to 30 degree with a radial line at P, which is r0 equals to 50 root 2 centimeter away from O. What minimum distance from surface of the sphere can the beam reach? So I have drawn a very rough diagram here, and just I have drawn this figure here once again, and this one is O. I haven't drawn this metallic sphere, so let me once draw this one, let's say of radius capital R. So the ray is incident at point P at an angle theta with a radial line. So as per our idea, this is the angle of incidence. So yeah, as per our idea, we will use that mu r sine theta will be constant. This is the concept that we have learned in this video. So mu is proportional to r, so I have written that mu r as k into r. K is some constant. So at point P it is incident at an angle theta, so sine of theta into r naught. So let's, as the refractive index is varying with the radial distance, we can assume the radial layers something like this, right? Because it is only the because the refractive index is only function of radial distance. So at a particular radial distance, all the points will have the same refractive index value. So we can assume this kind of several spherical layers having same refractive index. So it is coinciding with the concept that we have just learned. So sine theta into r naught, because r naught is the radius of the medium on which it is just falling on, and k r naught is its refractive index. And after a certain point of time, it will get a total internal reflection will happen, and the light ray will bend away from the point O. So at the point where the TIR will happen, or we can say that angle of incidence is 90 degree. So we can conclude that there the R minimum will occur at that point only, because after that the light ray will again move away from point O. So the distance will again keep on increasing. So at R minimum point I am writing the same equation, that mu r sine theta again. So sine will be sine of 90 degree, and R minimum into refractive index is k R minimum. So k gets cancelled, and R minimum comes out as r naught into square root of sine theta. And this is the distance from point O, but we are supposed to find the minimum distance from surface of the sphere. So from surface of the sphere we will just subtract the capital R, because this one is our required answer, and we have found out the R minimum from center O. So it is nothing but r naught root sine theta minus r, and I have not shown the calculation here. R naught is given, theta is given, and capital R is also given. You just put the values and you will get 40 centimeter, and this is the answer for this question. So that's all for today, and I'll bring some more interesting problems in the next videos, so stay tuned.